And now here summary. So far all have discussed, all are written here, so you can read them as a summary. Now the maths equations. So these all equations are written here, and I have shown you the derivation or how this expression came. So I think you can drive them in your home as well. Now we will focus on some examples. So first of all, example 21.1. So a series resonance circuit is given and some parameters are already given, for example R, XL, XC, and the first question you have to identify I, VR, VL, VC. So first of all, since this is a series resonance circuit, so ZTS will be just R, that means 2 ohm, and then you can derive the expression of I equal to E over ZTS. So E is 10 volt 0 degree, it was given, so you can put them, and this is just a simple calculation. Similarly, the VR equal to E. Why? Because at resonant condition, this VL and VC, there will be no drop to this end, and also the voltage will be all dissipated to a resistance. That means VR equal to just the same 10 volt angle 0 degree. And then if you want to calculate the VL and VC, so that VL equal to I into XL. Just the similar formula, that V equal to I multiplied by Z, right? So I was just I angle 0 degree, and you already calculated the value of I, and then Z equal to XL angle 90 degree. So if you calculate them, so final result will be just like this. Similarly, you can calculate the VC, that I into XC, and then the quality factor XL over R. So R is already given here, XL is already given, so you can calculate the quality factor just like this. And then the bandwidth. So far you have calculated QS, that is the quality factor, also the resonant frequency. I think it was given, yes, it was given in question number C, if the resonant frequency is 5000 Hz. So Fs was given, and you have calculated Qs, so you can identify the bandwidth at Fs over Qs. So answer came 1000 Hz. This is the bandwidth. And the half power frequency, at half power frequency the power is half of P max, that means since it is half power as the name suggests, so half P max, that means half of I max square R. So this I is basically the I max, that means the current will be maximum at resonant condition, and this current is basically calculated at resonant condition, so we can call them the maximum current. That's why I max, and the R was given as 2 ohm. So all values are calculated. And in our second math, I think you can also do them in home. Anyway, let me show you in brief. So resonant frequency is given, and you are asked to calculate QS, and also the bandwidth is given. So bandwidth was given, resonant frequency was given, you want to calculate QS. So obviously QS equal to Fs over bandwidth, so QS came 10. And then if R equal to 10, what will be the value of XL? So that QS equal to XL over R. So R is given, QS you already calculated as 10. So obviously XL you can calculate it just like this. And the third question, find the inductance and capacitance. So that the inductive reactance XL equal to 2 pi Fs into L. So L equal to XL over 2 pi Fs, so you can write this. So XL you already calculated in question B. Similarly Fs was given, so you can calculate, it was 3.98 millihenry. And similar manner you can also XC, you can also calculate this. And the third and fourth question, what are the probable commercial values? So commercial values means what are the values of inductance and capacitance that are available in market. Obviously that 3.98 millihenry, this will be tough, so you can approximate this to, let's say, 3.9 millihenry, because when 3.98 millihenry is required, I think 3.9 henry will suffice. So So that's why you can use it as 3.9 millihenry because it is available in market. Similarly, the second one 397.89, the close value to this is 390 nanofarad. That's why you can use it 390 nanofarad. So don't bother much about this last one. Example 21.3. so here also value of R and the resonance frequency is given, and you are asked to calculate the bandwidth. So bandwidth equal to Fs over Qs. So Fs was given, Qs was not, so you can calculate Qs equal to XL over R. So you can just calculate the bandwidth later, and then find the cutoff frequencies, that means F1 and F2. So here Qs came 60. So previously I mentioned that if Qs greater than equal to 10, then we can approximate at it as a symmetric, that means Fs is the mid value of F1 and F2. So since this is the mid value and this is the bandwidth, right? So this portion will be the bandwidth divided by 2, since this is symmetric. So we can write the F2, that means F2 will be Fs plus this bandwidth divided by 2, this F2. So we can write F2 equal to Fs plus bandwidth divided by 2. Similarly, we can write this F1 as Fs minus bandwidth divided by 2, since it is symmetric. Why symmetric? Because this is an approximation whenever Qs greater than equal to 10. Now example 21.4. Here first of all let me clear this. So here a graph is shown, and from this graph you need to determine Qs and bandwidth. So first of all, what is the resonant frequency from this graph? You can understand that this is the resonant frequency. So this one basically 2800 hertz, because this one 200, this is 2000, and this is 3000. So this point will be 2800 hertz. So this is our resonant frequency. And what is the bandwidth? So you know that the bandwidth generally appears at 0.707 of peak value. So peak value is 200. So if you multiply 200 by 0.707, then probably you will receive some values close to there, probably 141 or something. So anyway, so at this value, so you understand that if you draw a line, then this will be just like this. So this amount will be our bandwidth. So if you calculate this, consists of two horizontal box. So this will be 200 hertz, since one box is equal to 100 hertz here in this graph. So bandwidth equal to 200 hertz. So bandwidth and frequency, both of these two parameters are found from this graph, and then we can calculate the quality factor equal to Fs over bandwidth. And then the question number B, for C equal to 100 nanofarad, determine L and R for the series resonant circuit. So already know that Fs equal to 1 over 2 pi LC. So here C is given 100 nanofarad, and also you have determined the value of Fs in question number A. So Fs is given, C is given, so also you can calculate the value of L just like this. And again, you know that Qs equal to XL over R. So from this expression you can also calculate the value of R equal to XL over Qs. And our last question, determine the applied voltage. So applied voltage, you know that applied voltage equal to I into R, and at resonance condition this is I max. So I max multiplied by R. So I max is 200 milliampere and R is already calculated. So where do you find the I max? Here in this graph, this is the I max 200. Now example 21.5. So here some values are given. First of all, the resonant frequency 10 to the power 5 radian per second, and also the bandwidth 0.15 into omega s. So first question, determine the value of R. So here the power is given 16 watt, this is the power and this is the voltage, right? So power is given, voltage is given. So if you want to calculate the resistance, so you can use this equation, because power equal to E square divided by R, that means voltage square over resistance. From this expression you can calculate the resistance and it appears 900 ohm. Then find the bandwidth in hertz. So you know that Fs equal to first of all we need to calculate the bandwidth. So bandwidth is given here 0.15 omega s, right? So 0.15 omega s, and what is the value of omega s? Omega s equal to 10 to the power 5. So 0.15 then 10 to the power 5, and it is in radian per second, right? So it was radian per second, but you have to calculate it is hertz. So you probably know that omega equal to 2 pi f, right? So if you calculate it with hertz, then hertz equal to radian per second over 2 pi. That means you need to divide this one with 2 pi. So this sort of calculation is given here. So first of all, this radian per second is divided by 2 pi, and then this is multiplied by 0.15, because the bandwidth was mentioned as 0.15 into omega s. So now the question number C, find the nameplate value of L and C. So you have to calculate the value of L and C. So far you have also calculated the bandwidth and also the resistance. So the bandwidth expression R over 2 pi L, this expression was also derived when I showed you the expression of bandwidth. So bandwidth equal to R over 2 pi L, where we can write L equal to R over 2 pi into bandwidth. Then if you put the values of R then bandwidth, then you will get the values of L as 60 millihenry. And to calculate the C, we can use the Fs equal to 1 over 2 pi LC, that means the resonant frequency equation, where we can find the expression of C just like this. And the question number D asks you to determine the QS of this circuit. So QS, we know the formula of QS equal to XL over R. So we already calculated the value of L. So we can write XL equal to 2 pi Fs L, because XL equal to initially omega L, we can write then omega equal to 2 pi F. So it is 2 pi FL. So Fs is calculated here, and then L is calculated here, and also the value of R is given in the question here. Also we calculated the value of R in question number A. So it is not given, we calculated it anyway. So all values are available, so we can calculate the value of quality factor. And our last question asks us to determine the fractional bandwidth. So you know that the fractional bandwidth was F2 minus F1 over Fs. So it was just like 1 over QS, like, so 1 over QS, you already calculated the value of QS here in question number D, QS 6.67. so the answer of fractional bandwidth will be 1 over 6.67, that means 0.15. So far I have shown you up to this resonant condition. I think now we can end it here.